Chapter 4, we did all of it except 4.7. And the reason I held off on 4.7 is because I know that it leads into chapter 5, which is this week, starting tomorrow, really well. So we know that the periodic table has information that is organized in a way that has patterns. For example, you know where metals are and where nonmetals are, right? Yes. And they all said yes. Oops. Interesting. This periodic table has this bold in the wrong place. Except one of these touching the line. So there's metals on the left and nonmetals on the right, but there are a couple exceptions. What is the exception?
Aluminum.
Yes, that is one of the exceptions. Aluminum touching the line isn't a metalloid. It's a metal. And you know that because you have aluminum foil in your kitchen. So metals on the left and nonmetals on the right, except for one. What's the exception there? Hydrogen is on the left of that line and is not a metal. Hydrogen is a non-metal. So maybe I need to color code a little bit. When we made that periodic table, we said color all the metals red. I heard an O.
I thought you were saying the other side of the non-metal.
No, what you said was good and true. It wasn't where I was leading, but I was going to get there. You just got there before me, so it's totally fine. Okay, so typically, and we use red to indicate on that assignment I gave you a while back, you know, metals are on the left. And nonmetals are on the right, except for that one. And then touching the line, we have the metalloids. Boron, silicon, germanium, arsenic, antimony, tellurium, polonium, and astatine. Those are metalloids. So as we step into chapter 5, we're going to be focusing on metals, bonding with nonmetals, and those are called ionic compounds. I'll write that down in a second. And then when nonmetals bond with other nonmetals or metalloids, that's a different kind of bonding that is named differently, and that's called covalent. So back when I gave you the assignment to color your periodic table, it was for a reason. I wanted you to really have firmly in your mind metal, metalloid, nonmetal, whenever you look at an element, because it will help you through this chapter. The next thing I would say is there's a property of metals that is super important, and that is that metals lose electrons easily. And we have a word for that. We have a couple words, actually. You know how metals rust? That's because they're losing electrons to form an ion, a cation. When they lose electrons, we can say they are oxidized. Their oxidation number has gone up. And those will be words that we'll continue to use. Yesterday in Zoom, I had a student that was talking about just the language of chemistry, and I realized, oh yeah, there is a language, and that is a barrier for a lot of people. You're stepping into a science class that also uses math as a tool and has its own language. And so I want to comfort you that the words will start to be normal. It's kind of like we're in a language class and there's some immersion that happens, and there can be discomfort or anxiety about the immersion, like, should I know that word now? And when you have those moments, you can ask, and I'll say, don't worry, we'll keep using that word. But one student, in response to the question of, like, these words are confusing, how do I handle this? A student volunteered, well, I don't stress when I don't know a word, but I do look at the meaning of the word. And so this particular student was just saying that when they come to a word that is a sciencey word, they refer back to their notes. And I think that's one of the reasons that chemistry takes a lot of time, is because you are learning a language as you practice math, as you learn science. And so I'm going to use words like, when metals lose electrons easily, they oxidize. And you don't have to know oxidize today. There will be a point in the semester when we look at that a little bit more in depth. But I'm still using the word as part of the immersion of this language of chemistry. Okay, so metals lose electrons easily. And when they do, when sodium metal loses an electron, it becomes sodium ion. And a positively charged ion is called a cation. Okay, so a sodium atom becomes a sodium ion. What's the difference? The difference is in the number of electrons. So last week we looked at how do you know it's sodium? Because it has, I find it on the periodic table. Oh, it's element number 11. It has 11 protons. Having 11 protons makes it sodium, metal or atom or ion. An atom of sodium has an equal number of electrons. So here's sodium. It's element number 11. It has 11 protons. Each proton has a +1 charge, so there's a +11 charge in the nucleus. And then it has electrons. If it's an atom, it's going to have 11 electrons with a -11 charge outside the nucleus. How many neutrons does it have? We don't know. The number of neutrons depends on which isotope it is. But because neutrons are neutral, I don't have to know how many neutrons there are. They don't change the charge. So for a sodium atom, the overall charge is 0. For every atom, the overall charge is 0, meaning the number of protons equals the number of electrons. And the number of neutrons, well, that determines which flavor, which isotope we're talking about. But sodium isn't stable like that. Sodium is stable when it has 10 electrons. So if sodium, with its 11 protons, can lose 1 electron and only have 10 electrons, the overall charge is going to be +1. And we call that an ion. So a charged atom is an ion. Now, why would sodium do that? Why would it lose 1 electron? And it turns out sodium exists in 2 states, the atom, 0, neutral, and the ion, which is always +1. And one of the states is more stable, so that's how we find it in nature. We find sodium as an ion in nature. Sodium in your body is the ion that has a +1 charge. Why is that? And the answer is because there is something magical about having 10 electrons. Okay, so the periodic table has groups, and a group is just a column. And those columns are a column because they have something in common. And the thing they have in common is the number of valence electrons. And valence is a word that we'll encounter later. I'm just using it. That's part of the immersion. And valence electrons are outer shell electrons. We haven't even talked about shells yet. And everything in group 1 has 1 valence electron. So to become stable, it loses 1 electron and it has a +1 charge. If you lose something negative, an electron, you become more positive. So the families have family names. The first group was the alkaline metals. The second group is the alkaline earth metals. Here we have the halogens. And then finally we have the noble gases. So I want to focus on the last column, which is called group 8. Group 8 is really important. So group 8 is a family that's called the noble gases. They have another name, which is the inert gases. And inert is a fancy word that just means unreactive. So they don't tend to gain or lose electrons, and they don't tend to form bonds, covalent bonds with other nonmetals. Why is that? And the answer is because of the number of electrons. There is something special about having 2, 10, 18, 36, 54, or 86 electrons. And we'll look at that throughout the semester, and you'll see that in your next class as well. Whatever your next chemistry class is, that will be important. So you never have to memorize those numbers because you will always be provided a periodic table for a quiz or a test. And when you do homework, you have one available too. But what we need to know is there's something really special about those numbers. And so if a metal can lose electrons to become isoelectronic, with a noble gas, it will, and that's stable. Iso is a word part that means same, and the electronic part, it has to do with the number of and the arrangement of those electrons. So why does sodium lose one electron? To become isoelectronic with neon. Metals lose electrons to become more stable. Nonmetals gain electrons. They gain electrons easily. They have a high electron liking, called affinity, a high electron affinity. And so when a nonmetal gains an electron in order to become stable, it becomes an anion. An anion is a negatively charged ion. So metals lose electrons to form cations. Nonmetals gain electrons to form anions. And when they do, we have an ionic compound. And that's what I want to focus on. Okay, so in this chapter, chapter 5 and 4.7, 4.7 talks about what ions will form. And then chapter 5 talks about when they form ions and make compounds from that, how do we name that? So I want to explain what a compound is. I'm defining it, or giving the general idea. A compound has more than one element so more than one elemental symbol, and a net charge of 0. So this is not a compound because it only has one element. This is a compound because it has both hydrogen and oxygen, and I don't see any charge. This is not a compound. That's an atom that has lost one electron, so it has a +1 charge. That's an ion. This is a compound. It's made of sodium ions and chloride ions, but when they come together, they have no overall charge because the +1 of sodium ion balances the -1 of chloride ion. This kind of compound is made from hydrogen, which you know is a nonmetal, and oxygen, which is also a nonmetal. When we don't have a metal, we don't have any ions. And so this is a covalent compound. Here we have sodium with its +1 and chloride with its -1, but when they come together, we can't see the charges. We hide the charges and the charges add to 0. And so because we have a metal, and the metal has formed a cation, and we have a nonmetal that has gained electrons to form an anion, and we put them in a ratio where they add together to 0, that is an ionic compound. It's ionic because it's made from ions. So here's some important ideas. We're focusing on this today, ionic compounds. We're recognizing that metals lose electrons and become positive. You lose something negative, you become positive. Non-metals gain electrons and then they stick together. And when they stick together and the net charge adds to 0, we call that an ionic compound. And we're going to talk about how to name them. So first I want to go to your book. So right here, I'm in chapter 5 because that's where we are now. You are going to want to go back and read 4.7. 4.7 talks about how lithium is an atom. It's in group 1, it's an alkali metal. Can lose an electron and become lithium ion. And it's a positive ion, so it's a cation, and the charge is shown in the upper right-hand corner. And then they walk you through where the charge came from. And that fluorine gains an electron to become fluoride, and fluoride is an anion, and they walk you through protons plus electrons add up to the total charge. So you need to read chapter 4.7 at this time. But then we're in chapter 5. So I probably don't need to say this. And I certainly don't need to say it to the people who are here because you're here. I'm preaching to the choir here. But it is really important that you read the text for understanding, which might mean more than one, probably means more than once, that you watch all the videos, that you come to Zooms, and that you do all the work. So reading the chapter is not something you do if you don't want to watch the videos. You should do both. But anyway, they start with elemental sodium. And you've seen a video that showed how alkali metals react in water. They very quickly give off their electrons to water and form hydrogen gas. So elemental sodium is not stable. And elemental chlorine is also not stable. But when they react, so sodium is highly reactive and will produce hydrogen and set it on fire. Chlorine will rip your electrons off. There's a reason that we use things like chlorine for bleach or chlorine to sanitize. It's because it's good at grabbing electrons. But when they come together, they make something that is totally harmless. Sodium chloride, and that is an ionic compound because it has sodium, which is a metal, and chlorine, which is a nonmetal, that have gained or lost electrons, and they combine together. Okay, so there's the first page. And then I'm really just looking at the pictures here. And then they talk about molecules. And here we have some hydrogen is white and some oxygen is red. And I want to point out that hydrogen and oxygen are elements, but the way they're showing it here, they're representing it with 2 oxygens to form a molecule, 2 hydrogens to form a molecule. And the reason is because those elements are diatomic. They exist in pairs, and that will be something that we'll need to know, and we'll cover that in just a second. But then they can react to form water, and now we have 1 oxygen and 2 hydrogens that are sticking together as a discrete unit. So oxygen and hydrogen are both nonmetals. When they form water, when they react to form water, they create something that is a covalent compound, and there's a way of naming that. Okay, so chemical formulas, that's what we're practicing this week, how to represent formulas. They're going to talk about molecular formulas in the chapter, and they're going to show pictures that represent these compounds. Carbon monoxide and carbon dioxide are molecular because they're sharing electrons. We're not naming those today. And then how to write formulas. And so, let's see, hang on, I want to get to the picture. You can have a pure thing that is an element, and the elements are either atomic, they exist 1 atom at a time like neon, or they're molecular, they exist in pairs like oxygen. There are 7 that are molecular. That's a list you need to memorize today. That is something you need to know this week. And then there can be compounds, and we're talking about naming compounds. There's 2 kinds of compounds. There's the kind that's made from nonmetals only, or nonmetals and metalloids. By sharing electrons, that's molecular. And then there are compounds that are made when a metal loses an electron to form a cation, and a nonmetal gains an electron to form an anion, and they stick together. So this picture, I want us to focus on for a second. The difference between a molecular compound and an ionic compound, one of the differences, and important differences, that the molecular compound is a discrete unit. Here I have 2 hydrogens and an oxygen. That is 1 molecule of water. 2, 3. There are 3 molecules of water, and they are not connected because water can exist as a discrete unit in the gas phase, and that's what's happening here. But salts, ionic compounds, which are called salts. Here is an example of an ionic compound. An ionic compound is really a whole bunch of cations and anions that are locked together in a regular, repeating 3-dimensional pattern. We call that a crystalline structure. It's organized and they're sticking together because opposites attract and cations stick to anions. But when we give the formula, it's really just representing the smallest unit of a larger structure. Cation plus anion never exists as a discrete molecule like water does. It always is part of something bigger. Something like this, which is a fundamental skill, is that it's easy for students to Google answers. And so you just need to know that I, last semester, created a different periodic table, the periodic table of cats and dogs. Things in group 1, just like sodium and lithium and potassium and rubidium, all the elements that are alkali metals, are still going to form a +1 charge. Things in group 2, like the alkaline earth metals, are still going to form ions because metals are to the left of this line that have a +2 charge. Halogens, -1, -2. So there's a pattern that we're going to learn. And when I come down to testing you, I might have to test you with the periodic table of cats and dogs. So you actually are doing the problem solving on your own without the benefit of Google. So just know as you're learning this, that taking shortcuts would not be helping you. Don't do that. Here's magnesium. Magnesium is in group 2 and it's a metal. Metals lose electrons. When magnesium, element number 12, with its 12 protons, some neutrons, and 12 electrons, +12 charge in the nucleus and a -12 charge outside of it. This is an atom. When magnesium becomes stable by losing electrons, how many electrons does it lose? The goal is to become like the previous noble gas in its electron structure. How many electrons does neon have?
10.
Yes. So when magnesium becomes an ion, it still has 12 protons. It didn't become magnesium. But now it only has 10 electrons with a -10 charge. 12 plus 0 minus 10 equals 2. When magnesium becomes like isoelectronic with neon, it has a +2 charge. Magnesium ion always has a +2 charge. So here we have magnesium, the element, 1 atom at a time. And here we have magnesium ion. The only difference in their name is adding the word ion. And that's how it is for cations typically. So then there is a nonmetal. Let's look at a nonmetal. Like chlorine. Chlorine is a nonmetal. And chlorine has element number 17, 17 protons, some neutrons, and the atom has 17 electrons. So the atom has a 0 charge. But it turns out chlorine can't exist that way. It's not stable. So chlorine, the element, actually travels in a covalent way, sharing electrons with another chlorine. Chlorine, the element, is a molecule. And because it has 2 electrons, not 2 electrons, because 2 chlorine atoms stick together to become stable, like oxygen and hydrogen in the textbook, we say it's diatomic, 2 atoms that makes that molecule. So it is a diatomic molecule. There are 7 that are diatomic. It's a list that you need to memorize. Let me go ahead and show you that list right now. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. In fact, if you bring hydrogen over to the other place it belongs on the periodic table, hanging out with the other nonmetals, it kind of makes a 7. A 7 that start at 7. Or this week you'll see a video that has a mnemonic device. Horses need oats for clear brown eyes, or have no fear of ice cold beer, or the 7 starting at 7. So there's 3 ways that you'll learn to memorize the 7 diatomic elements. So chlorine isn't stable as an atom. Magnesium can be stable as an atom, but it's more stable as an ion. Chlorine can never just be an atom. It's a diatomic element, or it can gain electrons. There's 2 ways to become stable for nonmetals. They can share or they can gain. So, going back to chlorine, when it gains electrons to become stable, how many electrons will it have? What's the nearest noble gas? There's something super stable about having 2, 10, 18, 36, 54. So it'll become like argon. It doesn't become argon, but when it gains an electron to have 18, it now has a negative 18 charge. 17 minus 18 is negative 1. This is now called chloride. So for nonmetals, when they gain electrons, metals lose electrons, nonmetals gain electrons. When they gain electrons, their name changes actually. Chlorine becomes chloride. And chloride has a -1 charge because it needed 1 electron to be isoelectronic with argon, to have the same number, the magic number 18, like argon has. Okay, so now I'm going to look at magnesium and chloride coming together to form a unit. We know that magnesium is a metal. Metals lose electrons. Based on the periodic table, it's an alkali metal. It's going to lose 2 electrons. Every metal in group 2, every element in group 2, when it becomes ions, becomes a +2 ion. Chloride is a nonmetal that can become stable either by sharing electrons with another nonmetal or by gaining 1 electron. So when I put these together to form a compound, compounds have no net charge. I need to have them in a ratio that adds to 0, which means I need 2 chlorides for every 1 magnesium. So magnesium ion and chloride, 2 of them, form magnesium chloride. We don't need to say that there's 1 magnesium and 2 chlorides, because people who have a periodic table, they can look and understand that. Now, sometimes students will think, are you saying that the atom magnesium combined with a chlorine to form that? And the answer is no, because magnesium, if it's neutral, net charge is 0, and chlorine, if it's neutral, net charge is 0, there's no reason they would stick together. But magnesium ion is a positive ion, and chloride is negative, and they do stick together because opposites attract, electrostatic interaction. There's a potential energy lowering when these 3 ions stick together. Now, do we ever have just 1 magnesium chloride by itself? There's a magnesium ion, there's a chloride, another chloride to form a molecule? No, never. Ionic compounds don't make molecules. They exist in a crystal lattice, 3-dimensional arrangement with a whole bunch of magnesiums and a whole bunch of chloride ions. So that picture in section, I think it's 5.4 from the book, is super important for us to understand. For ionic things, metals and nonmetals that have formed ions and stick together, they stick together as a zillion of cations and a zillion anions, or in this case, 1,000 magnesium ions and 2,000 chloride ions make this chunk. But when we write the formula, we just look at the lowest whole number 1:2 ratio of cations to anions. And we always put the cations first. Okay, I'm ready for questions. Anybody? Anybody? Nope. Okay. Let's go back to the periodic table and look at something different. So let's say you had potassium as a metal, it's going to form a cation, and sulfur as a nonmetal, going to form an anion. What charge will potassium ion have? Right now it has 19 electrons, but 19 isn't stable. What number of electrons close to but less than 19 is stable? So argon is a noble gas. Why is it inert? Because it has 18 electrons. What's special about 18? We'll find out later. But the point is, 18 is a good number. So if potassium could lose 1 electron and only have 18, it would now have a +1 charge, and it would be called an ion, potassium ion. Sulfur is a nonmetal. Sulfur needs to gain electrons. How many electrons will sulfur gain?
16.
It has 16 electrons, but what would be a better number than 16 for electrons?
For it to be a negative,
17
17.
is more, but
Or
18 is beautiful. Yeah. So
18.
sulfur, which is element 16, has 16 protons plus 16 charge in the nucleus, some neutrons, but neutrons are neutral, and 18 electrons. It would have a -18 charge. What would the overall charge be?
-2.
So sulfide, because the name changes, has a -2 charge. So there's our anion, and here's our cation. Our cation is potassium ion. You can't call it potassium because potassium has 19 electrons, and this one doesn't. You have to call it an ion. And sulfur becomes sulfide. And we're going to put them together to form an ionic compound. So I've got potassium ion and sulfide ion. When they come together, they need to come together in a ratio, so the net charge is 0. That means I'm going to need 2 potassium ions for every sulfide.
Sue, are we supposed to see what you're writing right now?
Oh my goodness.
I'm sorry.
No.
There you go. There we go.
I'm sorry, because I was back on a different page doing all my writing, and you had no idea what I was doing. I'm so sorry. Thank you for
It's okay.
So when we name it, we're going to get rid of the word ion, and we put the cation before the anion, and then we just say what we have, potassium sulfide. Thank you so much. I really appreciate that, because I can see what I'm doing. Yeah. Okay, so this is an ionic compound. We always put the cation first, the anion second, just like they are on the periodic table. In fact, that's going to be a pattern. When you put things together, whether it is cation and anion, or whether it is covalent compounds like water, H2O, carbon monoxide, carbon dioxide, the one on the left on the periodic table typically is on the left in the formula and in the name. So that's good to know. Okay, so some of the metals, go ahead, is that a question?
Yeah. So for compounds, you always have a cation and an anion.
I think you might have walked in late, so you missed this sentence.
Maybe I did.
That's okay. No, for a compound, you always have more than one element and a net charge of 0. And then there's 2 kinds of compounds. On the left, I have covalent, nonmetals and nonmetals sharing electrons. And on the right, I have ionic. And that's all we're focusing on today, is how to name an ionic compound. So ionic compounds always have metals and nonmetals.
Got it.
Yeah. But the thing that they have in common is by being a compound, there's more than one kind of element. So for example, chlorine is an element, not a compound, because there's only one capital, there's only one kind of element there.
Mm-hmm. Mm-hmm.
And then they have an overall charge of 0. Now for things that are covalent, they're just sharing electrons. So the number of protons and electrons is the same, but they're sharing electrons. Kind of like if we were roommates and I had a coffee maker, you had a microwave. While we're in that cohabitation as a covalent compound, I have a coffee maker and a microwave. It's not really my microwave, but in that situation, it's like it's mine. So there's a sharing with covalent compounds. But ionic compounds have already gained or lost electrons, and now they're just sticking together like little magnets. Okay, so
Thank you.
You're welcome. So to summarize, hydrogen is not a metal, but it does lose one electron to form hydrogen ion. So that's a similarity. That's kind of why it's in that column. And then group 2 lose 2 electrons, and group 3, not boron because it's not a metal, but the other ones lose 3 electrons. But the stuff in the middle, how many electrons it gains or loses, we can't predict based on its position on the periodic table. And then nonmetals, these guys are perfect. They don't do anything, but halogens gain 1 electron, and then the oxygen family gains 2 electrons. The nitrogen family gains 3 electrons. Why the gaining and losing? To be isoelectronic with a noble gas, because that is the best way to be. But the ones in the middle, you know, how many metals they gain, how many electrons they lose, because metals lose electrons, depends on the metal. So here we have iron, and iron is element number 26.
Mm-hmm.
So it has 26 protons, or it wouldn't be iron. And it has some neutrons, depends on the isotope. And then it has 26 electrons, which is not stable. Iron rusts. It's going to change. So the atom has a net charge of 0, but when it forms an ion, it either loses 2 or 3 electrons. And there's reasons for that that we will look at later in the semester, but we don't need to look at now. For now, we just need to know that the elements, the metals that are in the unknown zone, the transition metals here and the inner transition metals there, they don't have a charge we can predict at this point. They have a charge that we just have to know. So because iron forms 2 kinds of cations, we have to tell people which one we're talking about when we name things. So I'm going to put iron together with fluorine here. So if I have iron 2, which is less stable than iron 3, and I combine it with fluoride, I'm going to need 2 fluorides for every formula unit, the unit that represents that bigger picture of the crystalline structure. And I put this 2 here. So what I have here is iron 2 fluoride. The name of this cation is iron 2. Why? Well, I have to state the charge in the name, or you wouldn't know because there's more than one possibility for iron. So now I'm going to do that same idea here, but instead of iron 2, I have a completely different ion, which is more stable, iron 3. So we need 3 fluorides to balance that +3 charge. And then that 3 is going to show in the formula as a subscript. So iron 3 requires 3 chlorides. This is iron 3 chloride. Oops, I didn't mean to do chloride. I meant to do chloride. Let me try again. Okay, so iron 2 and iron 3 fluoride, they're different compounds. The iron that you have in your blood is iron 2. It's in the middle of a hemoglobin group inside of red blood cells. And iron 2, once your blood is exposed to oxygen, let's say that you cut yourself and now you're bleeding, it turns from that sort of bright red color to a rust color because the iron 2 ion does something with oxygen in the air and changes to iron 3. So iron 2 is different than iron 3. It has different properties. It's far more reactive. It has a different color than iron 3. So they are different things. In the name, we have to state what they are because iron has more than one possibility. If it has a +2 charge, I need to say so. If the iron ion I'm talking about has a +3 charge, I need to say so. This business here is not referring to the iron's charge. It's referring to the number of the other ions that are required. This 2 is saying 2 fluorides are required to balance that iron 2 charge. Okay, other questions? That is everything for today. So tomorrow I'm going to post some videos on naming ionic compounds, and we'll have a worksheet that is practice. As you step into naming ionic compounds, a couple things to remember. One is it's a skill that you need. You won't always be online with Google, by your side. So it is a skill that you need. Second is it's frustrating at first. If there is a pattern, there is a puzzle, and at first nobody is good with this. But it takes practice, and this is my way of knowing if a student is hardworking, is by seeing how their nomenclature goes. So I picture the mountain of nomenclature. This is you standing at the base of the mountain, looking up, and it's foreboding. And the harder you work, the quicker you get to the top. So this is you in 3 weeks with ionic nomenclature and a big smile and your hair in the breeze. Victorious because you have done the work to conquer it. How fast you get up the hill depends on a couple things. One is how much this makes sense to you, like your natural innate ability to grasp this. But the other one is hard work. It just requires time. And what I've learned over the years is this is the first time in chemistry that people are like, oh my gosh, this is so much work. But it's worth it. And you have to do it because you're here, you want to stay, and you want to move on. And so there's ionic nomenclature, and then there's covalent nomenclature. And when we get to covalent nomenclature, there's really, there's more to learn. There's 4 different subcategories. So what I'm encouraging you to do is to dive in, to make the mistakes, to ask the questions, to do the practice, to get better, front load that work so that by the time you're doing it for points,